Detecting complex organic molecules would add weight to the idea that such chemistry is widespread and transferable between planetary systems, embedded in shared galactic space. For researchers still calibrating expectations, the fact that ThreeIAtlas is active now, while inbound and visible to sensitive instruments, marks it as a cooperative subject rather than a silent flyby. Even if its activity turns out to be limited, astronomers already have more to work with than they did for Oumuamua. The dust and gas it is shedding carry with them a record of a very different stellar nursery, one we cannot visit but can study through the sample it has delivered. Every telescope trained on it is, quite literally, capturing pieces of another system. Those pieces will not be simple to interpret. The first spectra will need careful analysis to separate weak emission lines from background noise, and to account for contamination by Earth's atmosphere in ground-based work. Confirming the presence of specific volatiles will require multiple, consistent detections over time. Changes in coma brightness or structure must be untangled from variable observing conditions. And all of this will be happening while the comet continues on a one-way path out of range. Still, this is exactly the window astronomers need to address one of the most compelling questions any interstellar object raises. With activity underway and tools in place to read its output, there is now a path to investigate not just how fast or how far ThreeIAtlas is traveling, but what it actually consists of. Facing the puzzle of composition. From the earliest confirmation that ThreeIAtlas had an active coma, attention turned to what that faint haze might tell us about the materials within. Its distance and speed hint at where it came from, but the nature of its ices and dust speaks to the environment where it formed. Composition could reveal whether this body mirrors the comets native to the solar system, or if it contains a very different mix of substances shaped in another star's planet-forming disk. Either outcome would inform how common certain building blocks are across the galaxy, and whether planetary systems tend to produce similar raw materials. The main way to probe that makeup is by studying the light from the comet. As sunlight interacts with its dust and gas, molecules in those materials absorb and sometimes re-emit light at distinct wavelengths that serve as chemical identifiers. Spectroscopy breaks this light into a spectrum, so researchers can search for patterns, bright lines or dark gaps, that match known signatures. Astronomers will be watching for water, carbon monoxide and carbon dioxide, along with organic molecules. Each of these has its own implications. Water suggests the body formed beyond a snow line, where temperatures were low enough for ice to remain stable. CO and CO2 can drive activity at much greater distances from a star. Organics point to chemical processes that might happen widely in protoplanetary environments. In practical terms, the work involves tracking very faint targets in challenging conditions. At its current distance, the coma is still small, and the gases present may be dominated by highly volatile species like carbon monoxide. Detecting them will require large telescopes, long exposure times, and steady atmospheric conditions. Near-infrared spectrographs are key because many of the vibrational bands for these molecules lie in that range. Instruments on the ground, such as Gemini South or NASA's Infrared Telescope facility, have already reported early near-infrared hints worth further checking. Observations from space-based telescopes like the Hubble Space Telescope and the James Webb Space Telescope are scheduled as well, using their freedom from atmospheric interference to search for weak emission lines with higher sensitivity. If water vapor appears this far from the sun, it would be a notable result, pointing to a fractured or highly porous surface that lets sunlight warm buried ice quickly. More likely, water-driven activity will increase later, closer to perihelion, with the early phase powered by other volatiles. By collecting spectra repeatedly, astronomers can watch the transition, building a profile of the comet's outer layers and deeper composition. Another target will be the complex organic molecules. These carbon-based compounds are common in many solar system comets, and are important in discussions about how primitive chemistry reaches young planets. Early follow-up spectroscopy aims to test for similar species in ThreeIAtlas. A positive detection would suggest that the chemical pathways leading to organics can occur under a broad range of stellar and planetary conditions, not just here. If absent, it might hint at differences in the chemistry of its home environment. Dust lifted from the surface offers a separate line of information. When sunlight bounces off these particles, it changes the light's polarization. By measuring that change, polarimetry can reveal grain sizes and surface textures. Combined with color and brightness data, these observations can narrow down whether the dust is rich in silicates, carbon, or other materials. Comparing these traits with known comets here will help determine whether ThreeIAtlas carries a familiar mix or something distinct. Extracting these signals is never straightforward. Reflected light from dust can mask emission lines from gas. Background starlight and Earth's atmospheric absorption need to be accounted for. The comet's motion adds another layer. Its velocity relative to Earth shifts the wavelengths of its features via the Doppler effect. Calibration must be precise to avoid mistaking noise for a real detection. Even so, a handful of clear identifications would be enough to reshape ideas about how much variation exists among interstellar objects. It is also possible that ThreeIAtlas could surprise us entirely. Observations of protoplanetary disks around other stars show a variety of molecules, some not familiar from our own comets. If such compounds are embedded in this nucleus, even in small amounts, they would expand the known diversity of materials forming around stars. But any such interpretation must rest on solid, repeatable evidence, which is why teams are careful not to claim results before the data are secure. The clock is part of the challenge. If early activity is driven by a thin layer of volatile ice, the coma could fade before inner layers warm enough to sustain outgassing. Missing that phase could mean losing the chance to identify certain compounds. That risk drives international coordination, with observatories planning overlapping wavelength coverage to minimize blind spots. Surface behavior brings its own variables. Gas jets can eject material unevenly, exposing fresh patches or sealing others under fallback debris. These shifts can alter the mix of gases and dust in the coma over days or weeks. Interpreting chemical changes, therefore, requires enough observations to tell apart surface geometry effects from actual compositional differences. Whatever the results, the conclusions will reach beyond this single object. If its spectrum broadly matches that of local comets, then the processes that shape icy bodies may produce similar results in many planetary systems, supporting the idea that the solar system's chemistry is not unusual. If, instead, significant differences appear, models will need to account for a wider range of possible building blocks and environmental histories. Both possibilities carry weight. Similarities would imply that water, organics, and certain minerals are widely available and potentially common in systems forming planets. Differences would underscore the diversity of chemical environments across the galaxy and raise questions about what worlds emerge from them. Even without samples brought to Earth, carefully gathered spectra can turn this fast-moving visitor into a rare probe of another star's formative processes. From here, the question is how its chemical fingerprint compares to the only two interstellar visitors studied before. Those earlier cases revealed their own surprises, one entirely without activity, the other behaving much like familiar comets. Where ThreeIAtlas falls between them remains to be seen. Comparisons to past visitors. The two previous interstellar visitors could not have been more different in behavior. Oumuamua, discovered in 2017, was small. Estimates range from just a few tens of meters to perhaps a few hundred meters long depending on the model, and entirely inert. No coma, no tail, nothing to suggest active outgassing. From the moment it was spotted until it vanished from view, it remained a point of reflected sunlight whose brightness shifted only because of its tumbling, elongated shape. With no gas or dust to analyze spectroscopically, its physical and chemical nature was left to be inferred from how it reflected light and how it moved. That absence of observable activity left the door open to many competing ideas about its makeup, from a rocky shard to an icy fragment coated in insulating material. By contrast, 2I/Borisov, which arrived in 2019, was unmistakably an active comet. It fell neatly into patterns familiar from native solar system comets: a bright, persistent coma surrounding its nucleus and a clear tail extending well away from it. Size estimates put it in the range of a few hundred meters to roughly a kilometer across. Spectroscopic studies quickly revealed water vapor, cyanide gas, and dust grains rich in carbon-based compounds. This activity and composition removed any doubt about its classification and gave astronomers the first direct sampling of interstellar cometary chemistry. With Borisov, the months-long period of visibility allowed researchers to measure how its gas production rates evolved and compare them to patterns seen in local comets. When 3I-Atlas was confirmed to be on a hyperbolic path, observers immediately framed the question in the same terms: would it resemble the quiet, enigmatic Oumuamua or the active, comet-like Borisov? Early imaging answered that very quickly. In the weeks after detection, telescopes recorded a faint but measurable coma and a short dust tail, even while it was still far from the sun. That placed it firmly on the active side of the spectrum, more in the style of Borisov than Oumuamua, and it meant the scientific potential would be determined by how much and for how long that activity persisted. The way these three compare in size is another notable distinction. While Oumuamua's elongated body likely measured only tens to a few hundred meters in length, and Borisov's nucleus fell somewhere between a few hundred meters and about 1 kilometer, 3I-Atlas has a far wider spread in current estimates. Upper limits from Hubble imaging place its diameter no larger than about 5.6 kilometers, while lower bounds, based on brightness and assumed reflectivity, indicate it could be as small as roughly 320 meters. Even at the lower end, it ranks among the larger confirmed interstellar objects, with the potential for more exposed surface to drive sustained activity. If it is indeed toward the larger extreme, the Coma could become significantly more extended and brighter than Borisov's, depending on ice composition and the distribution of active vents. Its early display of activity, while still several astronomical units out, suggests that some of its surface or near-surface ices are composed of highly volatile materials. In solar system comets, that often means carbon monoxide or carbon dioxide, which sublimate at much lower temperatures than water ice. Borisov displayed early signs of such volatile-driven activity as well, but its coma brightened in a steady, predictable way as it approached the sun. Whether 3I-Atlas will maintain that pace, surge early and then plateau, or accelerate further into perihelion is an open question, one which will frame how much data can be collected over time. Another axis of comparison is how long each object could be studied in detail prior to closest approach. Oumuamua, demure and inactive, provided no evolving features to track over time. Borisov's activity, by contrast, allowed a progressive record of gas output and dust production to be built during its inbound journey. Because 3I-Atlas was detected early and already showed signs of activity, its gas and dust production can be followed across a longer baseline than Borisov's, potentially giving the clearest picture yet of how an interstellar comet responds to increasing solar heating. The type of dust it produces may also set it apart. The short tail seen so far could indicate larger dust grains that persist near the nucleus without being quickly driven away by the solar wind, or it could reflect low ejection speeds at this distance. Borisov's dust tail was long and diffuse, pointing to a predominance of smaller particles. If 3I-Atlas is expelling larger grains, they can be distinguished by how they scatter sunlight, making it easier to separate their contribution from gas emissions in spectra. Polarimetric measurements, comparing the polarization of reflected sunlight at different angles, could reveal grain-size distributions and add another dimension to interstellar comparison. Even with all these similarities to Borisov's active state, there remain aspects where 3I-Atlas is its own case. Its record-setting velocity means it will spend less time in the zone where solar energy is intense enough to produce peak outgassing. For observers, that compresses the likely window for high-activity data collection. Perihelion may bring its brightest and most dust and gas-rich phase, but that phase could narrow rapidly as it leaves the sun's vicinity. Borisov's longer period near peak brightness gave astronomers more flexibility to schedule observations. For 3I-Atlas, planning must be more immediate. The contrast to Oumuamua is still relevant in a subtler way. One of the enduring puzzles from that first visitor was its non-gravitational motion, an acceleration that could not be explained by gravity alone, perhaps caused by outgassing too faint to detect. Debate about its cause continues. With 3I-Atlas, which is visibly active, any similar small accelerations will be easier to link to definite sources like jets or asymmetric emission. That comparison may help evaluate whether Oumuamua's extra push could indeed have come from hidden volatiles, or whether a different explanation is needed. At this stage, the most straightforward classification slots 3I-Atlas in with active interstellar comets like Borisov, while noting its exceptional speed and the wide uncertainty in its size. It has already answered the simplest question posed to any such visitor. It is not another inert, featureless object. It will provide measurable activity throughout its visible paths, giving researchers direct material to analyze. As the sparse catalog of interstellar objects slowly grows, these three cases outline the range of behaviors so far observed, from inactive and enigmatic to dynamically active and chemically rich. Oumuamua marks the quiescent extreme, Borisov the familiar cometary pattern, and 3I-Atlas is emerging as the largest and most energetically active example yet. How these differences connect to their formation environments remains an open question, one that can only be approached by comparing what each carries with it as it arrives. With its origin beyond the solar system certain, the next step will be to consider not just what 3I-Atlas is and how it behaves, but the long journey that brought it here. Understanding its incoming path may offer clues about the kind of stellar neighborhood it once called home, and about how common such travelers might be in the galaxy. A path from the galactic thin disk. Understanding where 3I-Atlas came from requires turning the usual approach to tracking comets on its head. Instead of projecting its route forward in time, astronomers work backward from its current position and velocity, running orbital calculations in reverse until the path extends well beyond the solar system. This backtracking reveals the direction from which it was moving before the sun's gravity shifted its course. For 3I-Atlas, those computations point to a radiant, the apparent source point on the sky, in the direction of the constellation Sagittarius, toward the Milky Way's core. That region lies along the dense plane of the galaxy's thin disk, where stars, dust, and gas are most concentrated. The radiant offers only a broad clue. For comets bound to the sun, it doesn't hold much meaning because their orbits eventually loop back to familiar alignments. For an object on a hyperbolic trajectory, however, it reflects its incoming path through interstellar space. Even so, it's not a pinpoint. The sector near Sagittarius spans a vast range of distances and contains countless potential source systems. Any apparent straight line from the current trajectory through that region inevitably blurs over deep time, because the galaxy itself is in motion. Here is where the limitations become clear. With an inbound velocity still near 137,000 miles per hour and an apparent hyperbolic excess speed of around 57 kilometers per second, 3I-Atlas would cover many light years in only a few 100,000 years. Over the millions and likely billions of years since it was ejected from its home system, the Milky Way's stellar disk has undergone continual dynamical changes. Stars orbiting the galactic center at different rates, gravitational tugs from giant molecular clouds, and the subtle but cumulative influence of passing stars. These processes make reversing the path to a single parent star essentially impossible. Each distant encounter would have altered its course slightly, and over cosmic timescales, those diversions accumulate into a trajectory that no longer points with precision to a launch point. Interstellar space is therefore better thought of as dynamically crowded rather than empty.